Okay, so now let's move on to part 2, which is domain adaptation. The idea here is that we have a source model that is trained on some source data, so denial of service attacks, and we want to use this model on our own data and see how it performs. It's not going to perform well, so can we modify the model so that it will perform well later on? Okay, so what are the data challenges that you can face with denial of service attacks? Well, okay, DOS attacks don't often label themselves. They're louder than most cybersecurity threats, yes, but it's not always clear whether or not a DOS attack is happening. Labeling, as usual, is expensive and time-consuming, and not every company has their own grad student monkey to work on this. Excuse me. Okay, so benign network traffic it's not invariant across different infrastructures. So we talked about this already. University students might be streaming videos, but in an enterprise, you just have a high SMTP load, okay? Finally, well, this results in misclassification when you're using external models. So you can't just grab a model, throw your data through it, and hope for the best. So the idea for this discussion today is coming from a paper on Archive, which attempted to do adversarial domain learning for denial of service attacks, and we're using the data sets that they also used in this paper, okay? So let's have a chat about the domain transfer. So now we're going to look at the second data set. So this is CSIDS 2017, which is from New Brunswick, Cyber Institute in New Brunswick. And we have the same columns of data. So we have duration, sent packets, interpacket arrival time, bits per second, and our label. And we even have a similar class ratio. However, this model does not perform very well. And you can also assess this from various different perspectives. So let's just say, for example, you didn't have access to how the source model's data was normalized. Okay, so it was normalized and then published, and you don't know what the original data, raw data, looked like. In that case, you can't normalize using their parameters, so you have to normalize your data using your own parameters. If you do that, the F1 score that you're going to get with this model is abysmal. You're going to get a target normalized score of F1 score of 0.03, which is way worse than random. If you do have access to the original source raw data, you can normalize the data, and you can normalize it using the same methodology, and you get a much better performance of an F1 score of 0.3, which initially seems great, but if you actually examine that, that's an F1 score of a model that always predicts 1. So it is pretty much the baseline that we need here. So that, again, is essentially a useless model. So we need to adapt this model so that it performs well with our target data. Okay, so what we're going to perform is adversarial discriminative domain adaptation. So this was from a paper in CVPR 2017. The idea is that if you have a model trained in one domain, you can, and you apply data from another domain to this model, it's going to perform poorly. So the example we have here is MNIST. On the left-hand side, you have some handwritten digit of number 8. And on the right-hand side, you've got the Street View household numbers data set. So these are printed numbers, color backgrounds, the domain is vastly different. So if you trained a number classifier on MNIST and then applied it to this SVHN data set, it's going to perform very, very badly. But what if we were able to modify the source model so that eventually, with this target data, the biases are corrected, and then we can actually do a much better job? Okay, so before we get into it, let's have a crash course in GANs, Generative Adversarial Networks. GANs are a two-player game. You've got a generator, you've got a discriminator. And the discriminator must differentiate between real and fake data. So the generator, meanwhile, is creating the fake data, and it's learning from the loss of the discriminator. So it's coming from a distribution of just pure noise. As the discriminator learns to distinguish between this noise and this data with some particular structure, So too is the generator listening to that loss function, and it's able to say, well, how about if I bias my generation towards something that is a little bit closer to the distribution of the real data. And eventually, so you can see here on the right-hand side, this GIF where you have this noise, it's just all fuzzy noise, and then out of the noise, you can start seeing vague shapes appearing, and then you can actually see eyes and noses and mouths and hair. And it's actually learning what a face looks like. So that's GANs. Typically, GANs are being used in images, but you can use them in more or less any data set, particularly any data set that is continuous. So eventually the generator is going to learn the data distribution. Okay, sorry, my throat is just going here. Okay. So adversarial discriminative domain adaptation is a variation on a GAN. And so from the paper, they have this figure that perfectly explains how this works. It's done in 3 stages. Stage 1 is pre-training. So you have your source data and you have a model. And so you train this model using the labels from the source data. In this case, they're using a convolutional network, but we can use pretty much any network you want. Okay. The second stage is to clone the model from the source model and remove the classifier. So now we're going to have a source model and a target model. And the source data is going to be fed through the source model. The target data is going to be fed through the target model. The output of both of these models then is fed into a discriminator. And that discriminator must decide which domain the data came from. So in this scenario, you're keeping the source model's parameters fixed. They're frozen, they're not allowed to change, but the target model's parameters are allowed to change. So the discriminator is learning to tell the difference between the source and the target model. But meanwhile, the target model is also listening in on the loss and is learning how to modify its values, its weights, so that the output of the target model will be indistinguishable from the output of the source model. Eventually, when this GAN has been trained, the discriminator shouldn't be able to tell the difference anymore. When this happens, you should be seeing roughly 50% accuracy for both sources. And this is the same thing that you would have in a GAN, where it's real or it's fake. When it's trained and it's stable, you should see roughly 50% accuracy for fake samples and also for real samples. The final stage then is to take your target model that has now been retrained, apply a classifier layer to it, and then put your data through it, and then assess what you have. So it's going to predict some of these rows are going to be denial of service attacks. So now you're going to have to go and investigate and see, well, okay, are these denial of service attacks or not? Okay. So just to give a little bit more detail on 2 data sets. So we have the UNSW MB15 data set, that's from University of South Wales, from the Australian Centre for Cybersecurity that came out in 2015. About 100 gigs of raw network packets, and there's a variety of simulated attacks, not just DOS attacks, where we're just going to filter out the DOS attacks for this. Then we also have one from the Canadian Institute of Cybersecurity in New Brunswick. This is about 50 gigabytes of network packet data. Because it came out 2 years later, you have a few more modern DOS attacks. And again, the idea here is that the domain is going to be slightly different than the previous domain. Okay, so let's have a look at the performance of the original source data. As we said, the class ratio is 0.2. We're using a very basic feed-forward network, and we get an F1 score of 0.77. We can actually get that up to, I think, about 0.8, 2 or 3 with the class weighting and the focal loss. So you can get a real performance boost just with those 2 parameters. But we'll just say for now that our F1 score is about 0.77, which isn't terrible. It's decent enough. But as we know, the F1 score that we got with the other data set is abysmal. It's either worse than random or it's just essentially random. So here's an example of training this adversarial domain adaptation. So these are our loss functions. The first 2 plots are the loss function of the discriminator, and the second one is of the generator. And the third plot is the accuracy for the discriminator for both classes. And so we can see that the the loss on discriminator is going down nicely, and then it starts to go up as it gets confused, and then the generator's loss goes up, but then it goes down as it learns to generate. And we can see a 10-fold increase in the F1 score, but again, it's not great because, as we already said, this F1 score of 0.3 is a baseline. We need to get better than that, which is kind of surprising because the curves here look really, really nice. Everything is telling the right story for GANs, but GANs are actually quite unstable to learn. So even if your accuracy is, both of them are reaching 50%, then, well, this still might not be enough because, for example, the loss here hasn't actually dropped that much. So the discriminator hadn't really learned that much. It's possible that you needed to train this for much longer until that you were sure that it had stabilized. So there's a few problems with this example of training. It gets even more challenging when we look at this example of training, which is extremely unstable. It's definitely probably never going to converge. But at the end of training, we got an F1 score of about 0.49. So that's significantly better. I guess the moral of the story here then is GANs are very, very fickle, and trying to ensure that they're stable is quite a challenge and is not something to be taken lightly. So the method that we're talking about today is very much cutting edge. It's probably not something you're going to employ anytime, say, this year in your role as a cybersecurity analyst. But it's possibly something that is going to be very, very useful in the next couple of years as GAN training matures and we're able to understand what are the methods that we need to use to ensure a stable training of a GAN. Okay, so the results, then let's have a chat about them. So we've seen a 16-fold increase in the F1 score without using any labels. So that is awesome. We're doing very, very well there. In fact, you can actually get the F1 score up to 0.6, right? Even though this is a very tricky thing to do, but we can get the F1 score up to 0.6, which is not far off the original F1 score of 0.77, which is pretty decent. You can also then, once you have adapted your target model, you can then use this as a launchpad for other methods. So you could maybe then move on to semi-supervised learning by saying, okay, let's look at these candidate labels. Let's assume that they're actually DOS attacks. Can we improve upon that? However, there are pitfalls in this methodology. So the first one would be that if you're moving from one data set to the next, you need to have expert domain knowledge. Because you're probably going to have to do some feature engineering. Some of these features aren't going to be the same. They're going to have different names. They might be in different scales. One might be on seconds. One might be milliseconds. One might be per second, per minute. It depends. And so you need to ensure that you understand the data sets very, very well and that you understand the domain very, very well. GANs are tricky. They're somewhat unstable. It definitely requires patience more than any other area in machine learning. And you need to understand such issues that you might come across, such as mode collapse or failure to converge. But as you gain expertise in this, it's something that you can be more comfortable using, then perhaps it's a tool that you can actually bring into your cybersecurity world. So, okay, in this example, we were actually able to assess the transfer performance because we did have the labels, but in reality, you will not be able to assess this performance other than actually going through all of the recommended high probability malicious labels and assessing whether or not those are true positives or false positives. Okay, so let's discuss what's going to come up in the workshop in the next couple of weeks. So in week 2, we're going to be talking about self-supervised learning and how you can perform an anomaly detection on unlabeled categorical data. So it's very difficult to typically do outlier detection on categorical data because it's hard to build up a good metric for this. But you can learn how to create realistic-looking negative samples, train a binary classifier with real data and the negative data, and then use that as a form of anomaly detection. So that's what we're going to be covering in week 2. We're going to be using the Los Alamos data sets, which is a wonderful data set. It has logon data, it has DNS data, it's got red team data, it's got everything you need. It has 1.5 billion rows, which is way too much data. So I've been spending the past couple of weeks sampling that and generating some fake data for you guys to work with in week 2. Okay, and then week 3, Sahara is going to be discussing anomalous behavior using trying to catch that using graph theory techniques. And so I'm really, really looking forward to that lecture and also to the workshop. So in the workshop themselves for week 1, you're going to be learning how to train the DOS classifier. You're going to be learning how to optimize that training. Then you're going to figure out which target features you're going to use for the adversarial domain adaptation, and then you're going to train the GAN to do adversarial domain adaptation. It's going to be challenging for sure. Might not work very well, but it's going to be really interesting, I hope, and hopefully it's going to give you guys some ideas on how you might get around not having labeled data. Okay, so I think I have like a little bit of time left. I might have rushed through that a little bit, I'm not sure. So I was said in the blurb that if there was time left on week 1, we might actually talk about adversarial attacks. So I'm very, very briefly going to talk about these. So adversarial attacks, if you're not familiar with them, have been a hot topic in machine learning for the past few years. Essentially, the idea is a small perturbation to the data, which you can see here on the right. So the data here is a photo of a panda, and the classifier is very confident that this, well, not that very confident, mildly confident that this is a panda. We add some tailored noise to this image. It's very, very, very small amount of noise. Visually, you can't actually see the difference of this noise being added onto the image. But now the classifier is saying that it's a gibbon with extreme confidence, 99.3% confident. So these small perturbations can lead to misclassification that to a human makes absolutely no sense. And also this misclassification can be targeted. So you can actually ensure that your data is misclassified as a specific thing. Now, typically this is applied in a white box context. So you're familiar with the model, you have access to the loss function, you're familiar with the training data, and you can really go to town on breaking that model. However, there are certainly attacks that have been made purely in a black box context, and you can do attacks via transfer learning and through all sorts of ingenious and inventive ways. Typically, though, the literature mostly focuses on images. So the question then is this a threat in cybersecurity? It depends on who you ask. A lot of people who are even experts in adversarial attacks seem to think that it is entirely an academic problem. It could be that, for example, if you had a model where you were asking outside individuals to upload images for your model to classify, well, then yes, you're absolutely at risk of an adversarial attack. But say, for example, the classifier that we were talking about today, denial of service attacks. Can somebody do an adversarial attack on that? They can't add a small perturbation to the number of packets that they've sent, right? They can't say I've sent 2.01 packets. They don't have control over a lot of the reality of what their attack creates. So, you know, those data points are gospel and they can't actually modify them. However, you could maybe, for example, grab this data set, train a classifier, and then do an adversarial attack on this classifier and see what features have to be modified so that the classifier misclassifies. And you might maybe determine that this classifier is very sensitive to high frequency attacks. So if there's a lot of packets coming in at a very high frequency. So maybe if you were doing a DOS attack, now you would say, well, if they're using the same data set, if I did a low frequency attack, maybe I would have a better chance of penetrating or effectively performing a DOS attack. Other examples are, you can have malware classifiers, for example, or intrusion detection systems, that anything that is, say, analyzing some string of code or input and trying to determine whether this is benign or malicious. One incredible adversarial attack that I've heard of with respect to these is where you have a malware classifier that is using a recurrent neural network, an LSTM, that takes in a sequence of, I don't really remember what the input was. It was code of some nature. It could have been in byte format or something. Takes in that sequence and then classifies whether it's benign or malicious. Somebody very, very easily broke this model by just stapling two malicious samples together, so it was extremely long. An LSTM, if you're familiar with it, actually has a short-ish horizon on how far back it can remember the data that it's seen previously. So somebody was able to override this model by just adding two malicious things instead of one, which is very, very bad. So then, but the classifier was able to actually thought it was now benign. So I guess the moral of the story here is that if you're training something in supervised learning and you're doing some kind of classification, and AI can really, really help you, machine learning can really, really help you, but it's also very, very, it's never going to be immune to further attacks. Whatever kind of solution that we think we are going to come up with, it's quite likely that somebody smarter out there is going to figure out a workaround and get past that. So ML is a great tool in cybersecurity, but it's not a silver bullet. So always know not to treat it that way. And if you have created something that is improving your security, try and think about it in an adversarial way. Try and think about a way of, well, how can I break this? In fact, you should be doing that for whatever classifier you're building, whether or not it's cybersecurity related or not. You should always try and figure out, well, how can I actually break this classifier? So we're not really going to go into any more detail on adversarial attacks. I just thought I'd like to mention it because it's a hobby of mine. And it's going to be something that I think is definitely a lot more of a threat in the coming years. So I do recommend you reading up on it and playing around with it, because it's a really interesting area and will be a threat in cybersecurity in the future. Okay, so I think that's me for today. So come back next week and we will be talking about anomaly detection using self-supervised learning. And then in week 3, we'll be looking at anomaly detection using graphs. Okay, all right, so see you guys. My throat.